Hello chemists, this is Ms. Placino and you are watching Screencast 3.3 on periodic trends. In the previous lesson we looked at atomic radius and first ionization energy as periodic trends, and today we're going to continue that discussion with a couple different trends. Remember, trends are just these patterns that show up in the periodic table as the elements are arranged in order of increasing atomic number. Two of the trends that we're going to look at today are electron affinity and electronegativity. So we can take a look at the do now real quick. Electron affinity and electronegativity are commonly confused for one another, and you can really see why. Both of them are talking about electron, the negativity, and affinity. That, I guess, kind of sounds similar to students. I don't want to get too much into explaining the difference right now, as this is going to be addressed in more detail during the lesson, but suffice it to say that they are not the same thing, and it's really important that you don't confuse the two. So let's go ahead and start off by talking about electron affinity. If you have an affinity for something, that means that you have a like for something. So in this case, we're talking about how much does an atom basically like to receive another electron. So our technical definition is the change in energy that occurs when an atom gains an electron. And this is also measured in kilojoules per mole. This really is the exact opposite of the first ionization energy. So if we think back to first ionization energy, we're talking about how much energy is required to take away the outermost electron of an atom. So basically how much energy is required to make a cation. In this case, instead of taking away an electron, we are trying to give an electron to the atom. It turns out that some atoms are happy to take it, and other atoms are not so happy to have this extra electron burdened, given to them. So what I would like you to do is think about what it might mean if electron affinity is negative, what it might mean if that value is positive. And we'll take it a step further. What type of elements would you expect to have a negative or positive electron affinity? And see if you can come up with why this is observed. So again, electron affinity can be positive or negative. If we think about first ionization energy, we know it's always positive. We know that energy is always required to take away an electron. So if we can kind of continue to use that rationale, if electron affinity is positive, we know that it took energy to give an electron. In other words, that atom didn't really want the electron, and you kind of had to force it to take the electron. On the other hand, if the electron affinity is negative, that means that energy was released to give atom, or I should say, when the atom gets an electron. So negative electron affinity means that the atom kind of wanted that electron in the first place. So when you gave it the electron, it actually released energy, meaning it made the atom more stable. I know that's a little bit confusing to think about, but stay with me. Positive means that it took energy to force the atom to take the electron. Negative means that the atom was able to take the electron and it actually made it more stable, so it released energy. So this really means that things that have a positive value for electron affinity didn't really want that electron, and atoms that have a negative electron affinity value must have wanted the electron. So if we get to this second question, what type of elements would we expect to see with a negative and positive electron affinity? Well, think about what we know about how metals and nonmetals react. If you have a negative electron affinity, again, energy is released. So we're talking about elements that want to get an extra electron. Those are going to be your nonmetals. And if you have a positive electron affinity, those are the elements that do not want that extra electron. So we're talking about your metals. And I guess we've kind of tackled this, why is this observed? Metals tend to give away their electrons, nonmetals tend to gain electrons. So if you're trying to force an electron upon a metal, you're kind of making it go against what it usually likes to do. And if you do the same thing with a nonmetal, well, that's exactly what it wants in the first place. Ionic radius isn't so much a trend that I want you to be familiar with, but I want you to think about what's going to happen to the size of an atom when it either loses an electron and becomes a cation, or it gains an electron and becomes an anion. So just for a second, pause the video and think about that. Would you expect cations to be larger or smaller than their neutral atom? And same question for anions. When an atom loses an electron to form a cation, the cation is smaller than the neutral atom. So for example, if we take sodium, which is a metal, we know metals like to lose electrons. Sodium on its own has an atomic radius of about 186 picometers. The sodium plus ion shrinks down to 97 picometers. So a pretty big drastic change in ionic radius in this case. The opposite holds true for anions. Anions are larger than the neutral atom. If we take chlorine with an atomic radius of about 99 picometers and we turn it into the chloride ion, Cl-, it nearly doubles in size. It's now 181 picometers. I'm not really concerned with you knowing exactly how much bigger or how much smaller the anions and cations are going to be, as long as you're comfortable with this idea that when I take an electron away, the ion is going to be smaller than the neutral atom, and when I give an electron to the neutral atom, the anion will be larger. If you think about why this occurs, it might be kind of obvious for some people. I've taken an electron away, so in the case of forming a cation, so now what can that nucleus do with the remaining electrons? Well, it's got one less electron it's responsible for, so it can pull the remaining ones even closer to the nucleus, making it smaller. When I give a neutral atom an electron and it becomes an anion, all of a sudden the nucleus is responsible for one extra electron. It's not going to be able to hold the electrons it has as tightly, so it's going to cause the ion to be larger than the neutral atom. So it's come up a couple of times now, this idea that metals want to lose electrons to become cations and nonmetals want to gain electrons to become anions. And I want to take a little bit more time just to discuss why that's observed. And it can really be explained through something called isoelectronic stability. I know that sounds confusing, but it's actually not so bad. Basically what this means is that elements in the S and the P blocks, so groups 1 and 2, and groups 13 through 18, want to try to attain an octet of electrons. We say octet, meaning a complete outer shell, or a full outer shell. And in the S and the P blocks, what a full outer shell looks like is 8 electrons. That's where the octet comes from. There's a certain amount of stability that's associated with having this sort of configuration. You filled up all the energy levels, or I guess more specifically the sublevels of that atom. So isoelectronic stability, again, just to repeat, it's stability that's attained by having an electron configuration that looks like a noble gas. So in the case of sodium, I've got the electron configuration 2, 8, 1. So in order to get an octet of electrons to complete its outermost shell, it can either try to gain 7 electrons or it can get rid of 1 electron. So hopefully you recognize the sodium atom is thinking, okay, just lose 1 electron. If I can get rid of that electron, oh my goodness, I can look like a noble gas, I can have a complete outer shell. Fluorine, on the other hand, is a group 17 nonmetal. It's got the electron configuration 2-7. It needs to get to a complete outer shell. It's probably thinking, and again, atoms can't really think, but if they could, it needs to gain 1 electron. It's like, oh, if I could just get that 1 electron, I could complete my octet and I could look like neon. So for this reason, elements like sodium and elements like fluorine are really, really reactive. They're kind of on the prowl to get rid of and to find that 1 electron so it can look like neon. This also explains why our noble gases are very non-reactive. There is absolutely no need for the neon atom to change. If it gains electrons or loses electrons, it's going to lose that stability associated with having a complete octet. I want to move on to our next trend, which is electronegativity. Not to be confused with electron affinity. They're different. Both of them are referring to electrons, but electronegativity is the ability of an atom in a compound to attract electrons from another atom in the compound. Basically, you can think about electronegativity in terms of tug of war. In order to play tug of war, you need 2 people. In order to play electronegativity tug of war, you need 2 atoms. They have to be bound together. And the people in tug of war are fighting over a rope. In electron tug of war, they're fighting over an electron. So certain atoms are going to be better at attracting electrons towards themselves in a compound than other atoms. From your reading, you should have gotten what the trend looks like as you go down a group and what happens to electronegativity as you move from left to right across the period. Pause the video, write down what you observe, and provide a brief explanation. As you move from the top of a group to the bottom of the group, we see a decrease in electronegativity. You've seen this picture a couple of times. We know as you move down the group, the atom gets bigger. Atomic radius increases. If we're talking about electronegativity, we're talking about the ability of an atom to pull an electron towards itself when it's in a bond. The way you're going to attract electrons to you is with your nucleus. And your valence shell, that outermost electron shell or ring or energy level, whatever you like to think of it as, is where the bonding is going to occur. So if I take another atom and I'd go to bond it to my original atom, look at how far away the nucleus is from the electrons that are being shared. There's no way that nucleus is going to be able to have a strong pull on the electrons that are being shared at this point. However, as you go up the group and the atom becomes smaller, all of a sudden that nucleus is closer to that shared electron, or the shared pair of electrons technically. So your largest atoms are going to have low electronegativities, and your small atoms, because the nucleus is close to the electrons that are being shared and therefore can attract it, should have higher electronegativities. As you go across a period, you're going to see that electronegativity increases. It's really the same driving force, but I guess instead of the atoms becoming larger and larger, you can think about the nucleus being stronger and stronger. We'll use these pictures again of our period 2 elements, boron and carbon. We know that as you go from left to right across the table, the strength of the nucleus increases and those valence electrons are placed in the same energy level. Since the nucleus is getting stronger and stronger, the atom gets smaller and smaller. And therefore, when we bond another atom to it, that very positive nucleus is going to be able to attract the electrons closer to itself. So if we just go ahead and bond another atom on top of it, because we've got a +6 nucleus in carbon and only like a +3 nucleus in lithium, the carbon nucleus is going to be much better at attracting the electrons in that bond towards itself than lithium can be with its, relatively speaking, weak +3 nucleus. Since this trend is all about ability to attract electrons to yourself in a chemical bond, there is a group in the periodic table that is largely omitted from this trend. Based on what we talked about in the last slide, hopefully you're coming to the conclusion that group 18 is omitted. Especially your really small noble gases like helium, neon, and argon, they do not form bonds with really anything. Some of the larger noble gases you can coax into reacting under extreme conditions, but generally, since these things don't form bonds, we don't talk about them in this trend. So our most electronegative atom on the entire periodic table is going to be fluorine. It is closest to the top, and it's farthest to the right, excluding column 18, the noble gases. We've got another graph for you to help you kind of visualize what's going on with electronegativity. I'll circle all of the group 17. There we go. We've got, as you move down the group, electronegativity is decreasing. And as you go across the period, you see electronegativity increasing. Electronegativity is not a measurable value. Basically, it is an arbitrary scale based on the number 4. So fluorine, they observed, is the most electronegative atom. It's the best at pulling electrons towards itself in a bond. So it was arbitrarily assigned a number 4. Then all the other electronegativities were assigned off of that. So for example, something like lithium is one-fourth as good as fluorine is at attracting electrons to itself, so it was assigned an electronegativity value of 1. Before we move on to any practice problems, I want to talk just a little bit about metallic versus non-metallic properties. You've got this table in your workbook, and I just want to work to complete it. Sometimes questions will be phrased, which of the following elements is the most metallic or the most non-metallic, and that can be a little bit vague. So let's talk about this together. If we think about our metals, the left of the periodic table, or the left of the staircase rather, on the periodic table, what do we know is true about their atomic radius? Basically, I'm looking for big or small. If you think about the atomic radius trend, you know that size decreases as you move from left to right. So our metals tend to have big or large atomic radii. On the other side of that coin, we've got nonmetals. They're the exact opposite. They're going to have very small atomic radii. Ionization energy. Because your metallic atoms tend to be large and hold their electrons far away from the nucleus, ionization energy of a metal tends to be low. Again, the exact opposite for a nonmetal. These are very small atoms with powerful nuclei, which make it very difficult to take away an electron. We just discussed the electronegativity trend. It's going to be the same as the ionization energy trend. And big metallic atoms, it's going to be hard to attract electrons to themselves in a bond. Small non-metallic atoms with powerful nuclei, they're going to be very good at attracting electrons to themselves. And finally, with the ions, we know that we're going to have cations forming. They're going to be smaller than the neutral atom. Non-metallic elements, they tend to gain electrons and form anions and end up being larger or bigger than the neutral atom. Great. So let's finish up with some practice problems, and I want to take a look at questions 2A and B. So pause the video, get out your periodic table, and see if you can rank these or order them from highest to lowest electronegativity. Okay, so I've got my periodic table pulled up. I'm going to just quickly draw my arrows to help remind myself. Electronegativity, we see increasing as we go across, and we see that it decreases as we go down. Order the elements from highest to lowest electronegativity. We've got magnesium, sulfur, aluminum, and chlorine. Just like with the previous practice problems that were similar to this, find the elements on the periodic table. Magnesium, aluminum, sulfur, and chlorine. Great, they're all in the same period. As I go across the period, the electronegativity increases. So we have to start with the highest and then go to the lowest, so we basically have to work in the opposite direction. So the highest one in this group should be chlorine, as it's the one that's farthest to the left. And then as I work backwards, I should get to sulfur, aluminum, and finally magnesium. For question 2B, I've got sodium, potassium, lithium, and rubidium. These are all group 1 metals. Sodium, potassium, lithium, rubidium. We want to go from highest to lowest. We know that electronegativity decreases as you go down a group, so the highest one is going to be the one at the top. So in this case, it'll be lithium with the greatest electronegativity, followed by sodium, then potassium, and finally rubidium. As with the last couple practice problems, oh, my dog's going crazy. You need to, or you really should, go through and take a look at practice problems C and D, try them out, and then check your answers against what we've got posted online. All right, keep practicing with this, and we'll talk again soon.